Hello, my name is Dragan Maksimovic. I'm a professor of electrical engineering at the University of Colorado Boulder. In this segment of the course, we are talking about a realization of the RACER air cleaner. A prototype of the cleaner is shown here. This cleaner was designed, developed, and demonstrated by a team of undergraduate students in the Electrical, Computer, and Energy Engineering department at the University of Colorado Boulder. The cleaner features low noise fans. It includes a replaceable MERV13 filter. It includes sensors for particulate matter, carbon dioxide, carbon monoxide, and air pressure. It is capable of manual or automatic control, and it has a very lightweight construction, make it easy to move from one place to another. Here is an electrical block diagram of the air cleaner. Central to the cleaner is a microcontroller that is controlling the operation of the cleaner. It is providing for a user interface, electronic control of the fans. It is communicating and collecting data from the sensors, and it also is controlling the power delivery unit. Air cleaner fans uniquely are based on the cooling fans for desktop personal computers. These fans are combined in an array of 6 fans, and they have electronically controllable speed so that the operation of the air cleaner can be adjusted depending on the sensed particulate matter, for example. They allow for fairly high airflow, up to 140 cubic meters per hour. And importantly, their operation is extremely quiet. So just the quietness of the air cleaner operation was important design feature. They are supplied from a DC voltage of just 12 volts with a low power consumption. The current of only 0.1 amp is necessary to run the fan. Among sensors, an important one is the sensor for particulate matter. And in particular, the particles of 2.5 micrometers should be detected so that filtering of the air can be done if the concentration of these particles is greater than about 12 to 13 micrograms per cubic meter. Just for reference here, you see a diagram that shows how small these particles are compared to particulate matter at 10 micrometers, like dust, pollen, and mold. PM 2.5 particles are what is a result of combustion, organic compounds, metals, and so on. The particular sensor that the team used in the realization of the air cleaner is shown here. It's a relatively low-cost air quality breakout board that uses laser scattering to radiate suspending particles in the air and then collects scattered light to be able to obtain the concentration of the particles. There is a built-in microprocessor that calculates the equivalent particle diameter and the concentration of particles with different diameters in the air. Air cleaner also includes a carbon monoxide sensor. Carbon monoxide can result from burning fuels, including wood, charcoal, gas, or propane. And increased carbon monoxide concentration can lead to carbon monoxide poisoning, serious tissue damage, and in high concentration, even death. The air cleaner cannot filter carbon monoxide, but can alert the user of increased concentration or the presence of natural gas. So it's a safety feature alerting the user of dangerous concentration of carbon monoxide. Our carbon dioxide sensor is also included. It's based on infrared detection of carbon dioxide. Outdoors, carbon dioxide concentration is between 300 and 400 ppm. Concentration above that may imply a high human occupancy in enclosed environment, in the indoor environment, which then can imply inadequate indoor ventilation and thereby increased risk of transmission of pathogens. So increased risk of transmission is associated with increased carbon dioxide concentration. Again, the air cleaner is not capable of filtering carbon dioxide. Carbon dioxide is just a gas, it cannot be filtered. But the air cleaner can alert users of increased carbon dioxide concentration, and the user may then open windows, ventilate the room to reduce the transmission risks. The air cleaner also includes a pressure sensor. In fact, two air pressure sensors. Two such sensors are positioned on opposite sides of the MERV filter. And the design decision behind that is relatively simple. It is used for tracking health of the filter. When an increased pressure drop between the two sensors on two sides of the MERV filter is detected, that is used to indicate to the user that the filter should be replaced. So this approach promotes ease of use and improved performance. It makes it relatively easy for the user to recognize where the filter has to be replaced instead of counting time, which is normally done with air cleaners. The sensors are integrated on two boards the team built. This is the main sensory array board on the left-hand side, and there is an auxiliary pressure sensor board for mounting on the opposite side of the air filter. For power delivery, the team used commercially available DC-DC converter blocks. The need for the power delivery blocks is because we have a DC microgrid of 48 volts available as the supply for the entire air cleaner. That supply of 48 volts can be obtained from a solar photovoltaic panel, from batteries, or from an AC outlet through an adapter. The system supply voltage requirements are lower, so we need a conversion from 48 volts down to 12 volts for the fans and for the LED emitting diodes that are used to produce ultraviolet light, and also lower voltages of 5 volts and 3.3 volts for sensors and the controller. This is the particular DC-DC converter block that the team used to realize this power delivery function. This block is producing regulated 12 volts at up to 4 amps of output, and the efficiency of the block is shown here. Efficiency varies depending on the output current